So in this video, we're going to talk about the normal distribution, particular standard normal distribution, and how to compute normal distribution probabilities. What's a normal distribution? Well, a large number of phenomena in the real world are actually approximately normal, or exactly normal. For example, the random variables of heights of people, or weights of people, or even scores of exams, birth weights of babies. They all have a common characteristic of being bell-shaped, with a center of mean mu and spread or variance sigma squared. More precisely, a random variable has x has a normal probability distribution with parameters mu and sigma, if and only if its probability density function has the following form: f of x is equal to basically e to the minus x squared. Okay? But this is centered around mu, by mean, and the variance spread sigma squared. In this case, x is called a normal random variable. And again, the area and total area on this curve is 1. And the curve is symmetric around the mean mu. As the tails go to 0 as x approaches plus or minus infinity. Okay. So as stated before, you can in fact calculate the expectation of x, right? The integral x f x dx from minus infinity to infinity, and show this is actually equal to mu. And of course, this is very hard. If you know anything about integrals, this is a non-trivial integral. Then the variance you can calculate as sigma squared. Our notation to denote a random variable following the normal distribution with mean mu and variance sigma squared is as follows. Okay. X tilde n mu sigma squared. Note here it's always variance in the second slot. We say here x. This represents the notation for x follows a normal distribution with mean mu and variance sigma squared. Now, random variable follows a standard normal distribution, means that it follows a normal distribution with mean mu equal to 0 and variance sigma squared equal to 1, or as we know already from discrete random variables, that in fact the standard deviation is just the square root of the variance. So a standard normally distributed random variable is one that follows a normal distribution with mean equal to 0 and standard deviation 1. So in fact, it's symmetric around 0 and has spread 1 if you want. Now suppose a normal variable z follows a... Oh, by the way, we reserve the capital letter Z to denote a random variable that follows a standard normal distribution. So that means Z follows n01. Now suppose Z follows a standard normal distribution. Now let's find, for example, probability that Z is less than 0.92, greater than Z is greater than 2.48, and so on and so on. Okay. So how are we going to do this? How are we going to find the area underneath this curve? Well, let's try B first. B. So B, we have, let's do B first. We want to find the probability that Z is greater than 2.48. Well, in fact, this is just going to be the area under the function fx equal to e to the minus x squared over 2 1 over square root 2 pi. Since z is a normally distributed standard normal distribution, so since z follows that, right, this means mu is equal to 1 and sigma squared is equal to 1. So we need to 0. So in this formula, right, mu equal to 0, sigma squared equal to 1, and so sigma is equal to 1. So that's why you have this. So this graph, in fact, so it looks like this, right? We find, so 2.48 is here. So how do we find the area to the right? Well, this means we need to actually find the integral from 2.48 to infinity at this thing, if you want to be precise. But this is impossible, okay? This is impossible to do. This can only be done using numerically, okay? So we approximate this using the normal table that is given. Okay? So we approximate this using the normal table, the standard normal table. What's the standard normal table? Well, so you might have encountered in secondary school or high school. It's also called the Z table. Some of you. So in particular, we're going to use the right tail table. This is the right tail table because it describes areas to the right of a certain Z. See the Z here? So how do we read this? Well, for example, first, we want to find the area. So in this case, we want to find the area to the right of 2.48, like in this picture here. So okay, so we go to our standard normal table. We look for 2.4. So on the left, you can see there's a 2.4. 2.4. You look at 2.4. Bam, right here, 2.4. So you can highlight it. 2.4. Maybe bigger highlight. 2.4. How do you get the 8? Well, you go up to the top, and you need to add a 0.08, right, to get 2.4. So then you highlight this. Then you go down the column, you go across in a row, and wherever it intersects is going to represent the area to the right of 2.48. So we have 0.00657. 0.00657. This can be 0.00657 by the table. Okay. Now let's get back to our A. What's the area to the left of 0.92? Okay, so you want to draw out what's going on here. These are standard normal variables. When area to the left, this is 0.92. So we want this area. But we only have a right tail table here. A right tail table. Right? This is only a right tail table. See, it's only right tail table. Area to the right of small z. So, well, by symmetry, the area to the left of 0.92 is the same as the area. Oops, sorry. This is 0.92. Sorry, we want this area. So this middle. So the area to the left is 0.92. is going to be, well, we know this is going to be 1 minus the area to the right of 0.92. This is little area here, 0.92. Because the total area underneath the whole curve is 1, we know. So we minus the small area to the right, 0.2, we're going to get this green area here. This is what we want. So this is going to be 1 minus probability that z is greater than 0.92. And we know this one. It's going to be, so 0.92. Look for the area to the right of 0.92. Let's erase this. So look for 0.9. 0.9 is here. And then we go across until we add a 0.02. Go down. And 0.1788 will be the, so this will be 1 minus 0.1788, which is 0.2. May I do one more example, but you basically see what's going on. Side of the page below. So, for example, let's do number 5. Oh, C, sorry. Let's do C. C. So probably that z is less than minus 1.62. Well, we draw this out. What's going on? This is our standard normal. This is minus 1.62. So we want this area then to the left. Okay. But again, we have only a right tail table. So how do we find this? Well, by symmetry, we know that this is it's symmetric around 0. So this is equal to the area to the right, this yellow area here. So in fact, this is equal to probability that z is greater than 1.62. And we can find this out here. We look for 1.6. 1.6 is here, and then we go across, and then again we go down 0.2, so that intersects at 0.0526. 0.0526. Okay. Maybe we'll do just one more. How about this F here? F. Well, so probably that z is in between 0.9. So the rest can be worked out similarly. 0.21. Again, let's draw this thing just to get you. So then we have this 0.21, 0.95. So we want this area here. Well, from the right tail table, you can see that this is just going to be this. You can compute this by computing the area to the right of 0.21. Then you can take away the area to the right of 0.95. See this one. Then what you're left over with, right? Because this is what you're left over with. This, right? This orange, this yellow area here. Right? So then this, what's the area? So this probably z is greater than 0.21 minus the area to the right of 0.95. Then you just read off this 0.21 is 0.21. 0.4168. 0.4168 minus 0.95. 0.95. 0.17. Plug that into your calculator, you get 0.247. Okay, so that's this, how you figure out areas under the curve with the standard normal distribution. Now, let's see how we can use this to find, also there's a typo here. It should be sigma squared. Suppose x follows a normally distributed random variable with mean mu. It's variance sigma squared. Then to calculate the areas of this normally distributed random variable, we standardize it, which means that we change variables to a standard normal variable by taking away mu and dividing by sigma, the standard deviation. Then you can show that in fact this translated and scale variable follows a standard normal variable. So if you want to figure out, for example, the probability that x is less than or equal to a, then you just standardize the variable to figure out the probability of the normally distributed random variable. The proof is just a change of variables form. For example, okay, so suppose, sorry, there's a typo here. That x follows a normal distribution with mean 30 and variance 10 squared. So that here, mu is equal to 10 and the variance is 10 squared. Let's find the probability that x is in between 30 and 49. And let's find the probability that x is in between 25 and 38. Okay, so let's change variables. Okay? So let's do a first. So the probability that x is in between 49 and 30 is equal to, so then we normalize. Okay? We change variables to standard. So this x minus mu is 30. So then we do the same thing on the boundaries too. That's 30 minus mu, which is, this is 30. So 30 divided by sigma, which is 10. Okay. And this is 49 minus 30 over 10 too. Okay? Because sigma is equal to 10. So sigma is equal to 10. So then this is fact this variable in the middle is your, it's supposed to be sigma. In the middle is your standard deviation, and this whole expression is in fact just the standard normal variable. So then we have probability, we calculate this would be 0 less than equal to z less than equal to 1.9. And we know how to figure this out. This is so we draw out what's going on. This is just the area to the right, in between 0 and 1.9. This area here. Well, how do we figure this out? Well, we know that the area to the right of 0. Area to the right is 0.5. So this is 0.5 minus the small area that's here. Minus the small area that's here. This area, small red area, is probably said it's greater than 1.9. So from a right tail table, we can read this off as so we look for 1.9. 1.9 is right here. 0.02 0.227, which is 0.4793. What about B? So we want to find the probability that x falls in between 38 and 25. Well, this is just again we normalize. So 25 minus 30 over 10. Let's give it a z. Let's give it 38 minus the mu, which is 30 over the standard deviation 10. It's probably that z is in between minus 0.5 and 0.8. Once you plug it into the calculator, how do we figure out these areas? This again, we just draw it out again. It's the normalized framework. This is minus 0.5 here. That's 0.8 here. So we want to find the total area from here to here, and also from here to minus 0.5 to 0. So the green area will be in fact just 0.5 minus probably that z is greater than 0.5. And then so this is the green area. The yellow area will be 0.5 minus probably that z is greater than 0.8. Then so then you can figure this out later. So use your check tables. It'll be in fact 0.4796. Okay. And our last. So now let's determine a z such that the area under the standard normal curve between 0 and the small z is 0.3212 and z is negative. So how do we do this? Well, let's see what's going on. First is the standard normal. And this z is negative. So that means z is somewhere here. Small z, it's a small z, okay? It's negative. Then the area between 0 and the small z, so here's 0. And we represent this area in yellow. Area here, so we know that the area in between the small z and 0 is 0.3212. This is the yellow area. But by symmetry, since this small z is negative, then minus z must be positive. Right? So this minus z is here, and it's colored green. So the yellow area is actually the same as this green area here by symmetry. So in fact, we have that the area in between the small z and 0 is equal to the area in between 0 and this minus small z, which is positive. This is this green here. This yellow represents the yellow area. So then, how do we figure out the green area? Well, the green area is just 0.5 minus the probability that capital Z is greater than minus small z. And we know that this area is in fact just 0.3212. Okay, so let's look at this equation right here, box in red. Well, solving for this expression in orange, in this red box, we get that probability that z is greater than minus z must be 0.5 minus 0.3212, which is 0.1788. So that more clearly, probably that z, capital Z is greater than minus small z must be 0.1788. So that means, looking at the right tail table, what? So is there any area to the, so is it this, okay, let's just erase everything first. Is there any area here to the that is there any z that has area to the right equal to 0.1788? Let's look for a 0.1788 anywhere. 0.1788. Oh, bam! Right there. 0.178. That means this mine, so this area to the right of 0.92 is 0.1788. So that means that this minus set must be equal to 0.92 by the standard normative table. So that means that this small z, after we negate both sides, is minus 0. So this small z here is 0 minus 0.92. We'll do our last example. So suppose, again, there's a typo here. It's supposed to be square here. Now suppose let x denote the amount of radiation that can be absorbed by an individual before he or she dies. Assume x is normally distributed with mean 500 roentgens and standard deviation 150 roentgens. So roentgen is a unit of measurement for X-rays. Above what dosage will only 5% of those exposed survive? Okay, so let's see what's going on here. So let X denote the, again, amount of radiation that a person can absorb before he or she dies. Before he or she dies. Okay? Then we know that X follows a normal distribution with mean 500 roentgens and variance given 150 roentgens. We want to find a K. Okay, so we want to find a K such that only above, so this, say this is 500, or this is the mean. We want to find a K such that to the right of this K is only 5%. Only 5% of the area. Okay, to the right. So only 5% people survive. I'm going to find a K such that probably that X is greater than K is 0.05. So how do we find this small k? Well, we normalize because we don't know how to calculate the area underneath a normally distributed random variable. But we know how to calculate the area underneath the standard normally distributed random variable, which is z. So we normalize k minus mu, which is 500 over sigma, which is 150, standard deviation is 0.05. So let's look at the table again. Is there a z such that the area to the right is 0.05? Is there a 0.05 anywhere in standard 0.05? Oh, bam! So almost here, 0.05. Not quite 0.05. And then there's 0.0495. Okay, so it's kind of somewhere in between here. Okay, so in fact we can. So it's like 1.6. So in fact, we'll accept any number on your midterm or final exam or assignments that's in between 1.64 and 1.65. You can also pick just somewhere in between 1.645. So that means that this k minus 500 over 150 must be equal to, so any number, in fact, any number in interval, the closed interval 1.64, we will accept any number, any closing number. So let's just pick 1.645, the middle. So solving for k, we must have k is 500 plus 1.645 times 1, which is 746.7. So above 746.75 Röntgens, that person will die being exposed to this or more